Jack's title for the talk is Return to the Moon, What It Was Like and What It Will Be Like.
Okay, thank you. Thank you, Ben. We've already talked, could we get some of the lights down a little bit because you're getting some reflections and they've seen me, they don't need to see me again. That's great. Now, we've talked about the Saturn V, and you'll get exposed to it some more. It is still the largest vehicle ever to put human beings in space. It weighed about 6.8 million pounds. The thrust of the first stage was 7.5 million pounds. Just a really remarkable accomplishment, and had a great deal more to offer had we been wise enough to proceed to amortize the investment that we had in it. Next slide. We talked about the training already, so I'm not going to repeat that, but this gives you maybe a visual feeling for what a simulation was like. Gene Cernan and yours truly working with mock-ups of backpacks, but with the real hardware there, and all in the positions where we expected to have them while we were suited on the moon. Again, one purpose of the training was to become so familiar with the equipment and the procedures and the sampling techniques and the documentation of samples that it was essentially second nature. The other purpose, of course, was to build insight into the crews so that they could make good judgments on what samples to bring back. You could always just go out and shovel 100 kilos worth of samples into a bag and come home, but that wouldn't have given us nearly the information that we ended up with as a result of the what we call selected sampling that the crews did. Next, please. Now, I'm not showing this just to show how much I aged over the years. But a lot of the young people are always wondering, what in the world are all those connections and blue and white things on the suit? Well, blue means something's going into the suit, red means something's coming out. That's the broad picture. In the upper right is the communication connection. There is the others are oxygen. The other two are oxygen connections, both emergency and regular. The right in the middle is the water connection. Now, some of you probably have forgotten or did not know that we used water-cooled underwear. In addition to our very cool personalities, the water really made a difference. In fact, we often talk about enabling technologies. We would not have been able to explore the moon for any length of time without water-cooled a system like that. It really made all the difference in the world, both for Apollo 11 and for the subsequent missions. We actually spent over 8 hours suited in this, and your body heat as well as the limited amount of solar heat would have just overwhelmed you very quickly. So that's a very important connection. The red, that bracket up in just under my name there is where we attach the one of the control unit for communications, and also the camera was then attached to that as well. The red one of them is an exhaust port if you had to use your emergency oxygen supply, which was a high pressure bottle, and the other one is the normal exhaust, recirculation exhaust for the oxygen that was coming into the suit, taking CO2 out, and then that was cleaned up in the backpack. Now we cool the water. I didn't mention that, but we cool the water by sublimation of ice through a porous plug. I'm not going to go into it in any more detail. But the principle is the same as evaporating water. But when you're in a vacuum, you can't evaporate water because water will freeze instantaneously when it's exposed to the vacuum. So the very clever engineers worked out a way in which you expose the water to vacuum, but in a porous plug, so you don't lose it, and then you let the sublimation of that of the ice that forms in that plug cool the rest of the water system. So it was a very clever design. It's still a very viable kind of way in which we're going to stay cool, I think, in the future. I don't know that anybody's come up with a better way to do that. Next, please. I like to show this picture. It's just another picture of Saturn V, of course, but it helps for perspective if you know that that's a very large fire engine down there in the lower right. The vehicle assembly building was the largest enclosed space in the world for many, many years. I think it was surpassed by the Mall of America when it was built. But I don't know what that tells us, but nevertheless, it tells us the Mall of America is awfully big. Again, 364 feet high, and you had the other numbers already. Next, please. This is that point in the mission that I was talking about, where all 5 F1 engines are banging away, and they're banging each other, and you get that very heavy vibration up through the stack, and you really notice it. The acceleration at this point is essentially very little. It's near zero. A very, very slow acceleration. In fact, it took about 14 seconds for the rocket to accelerate the length of the rocket. So it was mostly an acceleration experience. And you've seen that one thing that the Apollo 13 movie did extremely well. In fact, I thought they had figured out a way to enhance old photographs, but they did indeed simulate the ice coming off the side of the rocket. Those of you that have seen the Apollo 13 movie, early on in the launch sequence, you see that ice coming off. Well, there was ice, and particularly on our mission, there was ice because we were delayed on the pad for 2 hours and 40 minutes. And the Florida atmosphere, water in the Florida atmosphere condensed continuously on the side of the rocket because of the very cold oxygen and hydrogen tanks. And that does come off, and we'll talk a little bit more about that in a few moments. The next, please. A little farther away, and you can see some of that ice coming off even in this picture, breaking off. But the vibration is what primarily knocks it off. Next slide. Next, please. And then, of course, the more distant shot of the night launch of Apollo 17. I understand it was spectacular. I'm not really sorry I missed it, but I do understand it was spectacular. Next, please. One of the early views, we had 2 orbits of the Earth. Of course, the orbital velocity was the same as for the shuttle, and pretty much, and about 18,000 miles an hour. But we only had 2 orbits of the Earth before everything had been checked out in the S4B, the third stage rocket that had inserted us into orbit, and then we were going to restart that in order to accelerate to 25,000 miles an hour and go to the moon. But we had a little time. I had a little time to look out, and I'm going to take a few photos like this. It's not an ice pack. They're actually clouds. But what I really want you to note for later reference is the blue band at the horizon. That's our atmosphere, folks. It's a very resilient atmosphere. It's remarkable how resilient the Earth is in many regards. But that is still what, for perspective, is what makes it possible for us to be here. Just that little blue band. Next slide. Now, the first task that we had, and Ron Evans, of course, the other man on our crew, command module pilot Ron Evans, was responsible for docking with the lunar module that was up to this point stowed away in the end of the S4B. And there you see still stowed there, and Ron coming in to dock with it, and so that we could take it with us to the moon. That was important. Also, you note all around the S4B these pieces, these bright spots. And again, I think it would help if the lights could come down even more. These are dark pictures, and it helps to get those lights down. Those are, again, pieces of ice. The S4, not all the ice on the S4B had shaken off during the launch. And when we shut the S4B down after the burn to put us on a trajectory to the moon, there was still some, and it came off because that was a fairly abrupt shutdown. and was tracking with us on the way to the moon, this little cloud of ice particles. It really did attract our attention. It may be that this is what John Glenn saw over Australia when he reported seeing fireflies. But then again, he is the former Democrat senator from the state of Ohio, and that might explain that more than ice. Next slide. I couldn't resist, folks. John and I had a little bit of fun in the Senate every once in a while. We did overlap. This is that picture of the Earth that I mentioned that's so frequently requested from NASA. It really is a delightful picture, all the way from the South Pole up to the Mediterranean. Not really a full Earth, but as close as we were going to get by the Apollo trajectories. Africa, if you look closely, you'll see up in the upper right, there's a cyclone or hurricane going ashore on the subcontinent of India. Oh, great, thanks. I have one in my briefcase. Of course, it's always in my briefcase. I never get it out. Right there, and these fronts, arrowhead-shaped fronts going around their source in the southern hemisphere. Next slide. Now, we got to the moon in a hurry. 3.5 days. In a hurry tonight. I enjoyed every minute of the flight to the moon. Maybe it was mostly anticipation, but I was having a great time. But once we went into orbit around the moon, and this picture was actually on the far side of the moon, it's a lunar sunset terminator, a spacecraft sunrise. We were in what the astronomers like to call a retrograde orbit, actually going around the moon opposite to its very slow rotation. We didn't lose much energy in doing that, but it was important in order to have the sun behind us during the landing of the lunar module. We wanted the sun, we didn't want to land into the sun, we wanted the sun behind us and at an angle where we had good shadow definition of boulders and craters. So there was method in our madness of doing this. So we actually led the moon, coming from Earth, we actually went into orbit ahead of the moon and then made the burn of the service propulsion system in order to keep us in that orbit. Now this is a pretty good visualization of the color that we saw on the far side, slightly tan. Most of the far side highlands give you that slight tannish color. But I want you again to recall the band of blue around the Earth. Nothing. No atmosphere around the moon. No sensible atmosphere. In fact, the vacuum, and those of you who like to know numbers, is 10 to the minus 12 torr at the surface. It's a hard space vacuum is what it is. And so you're not going to see that kind of atmospheric band. Now, there is a little bit of a sodium atmosphere around the moon, but you do not see it. You see it only through spectrographic analyses. That's a transient atmosphere. It's sodium that's coming off of the minerals of the moon, stimulated by the impact of solar wind protons, as a matter of fact, but that's probably a different lecture. Next, please. There's the old Challenger. One of the most interesting questions I've ever had from a young person was, why did we put pizza on the legs? Whoops, there you go. It was a very, it was about 14 metric tons, if I remember correctly, at this point, fully fueled, ready to go down to the surface of the moon. We had an interesting exercise for Apollo 17 that nobody else had to worry about, and that is that because we were going into this deep mountain, narrow mountain valley, we needed to improve the knowledge, the lunar module's knowledge, computer's knowledge, and guidance system's knowledge of where it was in space, so we could keep a very tight control over that landing. And that was actually done by the ground, mission control, entering information into our state vector, our guidance and nav system, after they acquired us on the orbit that we actually landed on. So there's about a 14-minute window where they could get that information, that new information, updated information to us. And it worked. As a matter of fact, the navigation on all the missions except possibly Apollo 11, which we weren't really trying to pinpoint land, it worked beautifully. And every crew, when they pitched over, and actually knew where the computer was taking them. There was a grid on the window of the commanders called the COAS, and I always forget what the acronym stands for. Somebody here will shout it out probably, but the grid that you could use to tell where the computer thought it was going to land, and every time it was right where we had planned to land before we left the Earth. A really remarkable tribute to the all the mission planning and analysis people and everybody else that made that kind of navigation possible. Next, please. The Valley of Taurus-Littrow is that deep, is that bay-like indentation into a ring of mountains around one of the large basins on the moon called Serenitatis. That basin's about 740 kilometers in diameter. It is one of the last 14 young, large basins that formed on the moon. And it is in the knowledge of those basins and the ages of their formation and the nature of their formation that we have gained a great deal of insight into the history of the Earth about the same time, about 3.8 billion years ago, where the similar kinds of impacts were occurring on the Earth. We don't see the direct effects of those impacts, with one exception that some people have come up with recently, but nevertheless you know they happened. The Earth and the Moon have been tied together for 4.5 billion years, and so anything that, any objects that hit the Moon, similar objects were hitting the Earth. That valley's about 35 miles long, about, as I said, 4.5 miles wide, and the mountains go up to 6,000 to 7,000 feet. That picture is taken from about 100 miles away, nautical miles away. I should explain to you right now that I'm going to use all sorts of different units. The fellows in the audience here who worked Apollo built the Apollo systems using the English system of measure. We flew them using the nautical system of measure, and we worked on the moon using the metric system of measure. Somehow we got it right. We kept track of all of that. So I tend to mix them up, and I apologize if it gets a little bit confusing. Next, please. Now from about 15 nautical miles away, this is the Valley of Taurus-Littrow, and it's nice to have a pointer because our landing point was going to be right in there, in that cluster of craters. And that cluster of craters, we now fairly confident, were formed by by material that was thrown from a crater known as Tycho, about 2,000 kilometers to the southwest. And one of the things that the impact of that material up here on this mountain, the South Massif, triggered a landslide, an avalanche really, and that's what that plume-like deposit is right there. Is an avalanche that was almost certainly lubricated, if you will, by hydrogen derived from the solar wind. As it started to move, that hydrogen was released and did increase the fluidity of the landslide itself. Much like snow avalanches, as a matter of fact, where air does the same thing. Next, please. Well, the lunar module pilot doesn't get to look outside very much, so I saw you saw that earlier picture was pretty much what I saw before we started power descent. This is what I saw after power descent. My job was to make sure that the commander had information off the computer that would tell him, on the one hand, where he was going, using that grid that I mentioned earlier, the COAS, and on the other hand, gave him information as we got closer and closer to the surface on what his velocity rates were, both in altitude and side to side and front to back. And so we didn't have heads-up displays in those days. And certainly in the future Altair landing vehicle, I think both windows should have heads-up displays so the lunar module pilot can see a few things, but also participate in risk assessment and things like that. The base of the mountain there is about 3.5 miles away from the lunar module in the foreground. It's a very typical surface that several of the missions saw on the Maria. The depth of the regolith here, of the debris layer that covers that surface, is probably averages about 9 meters. It's a little deeper here than elsewhere, probably for two reasons. One is you've had debris thrown into the valley from the mountains on either side, and then we've had these eruptions of volcanic material, the so-called orange glass in the valley. There was black devitrified orange glass as well, and that has added material to the regolith. So it's a little deeper than, say, where similar aged lava flow had been pulverized at the Apollo 11 site where Neil Armstrong landed. That metallic object in the foreground is one of 16 small restartable thrusters that we use to control the vehicle during powered flight. It had a thrust of those had a pulse thrust of about 50 pounds. Again, compare that with the 1.5 million pounds thrust in the F1 engines, and you see the spectrum of thrust technologies that were developed, propulsion technologies that were developed for the Apollo program. Next slide. There, a better view of the lunar module from one of those pictures that I took when I finally moved away and had a chance to see our spacecraft in this magnificent setting that we had been privileged to go to. Next slide. And anytime you felt a little bit homesick, you could look up and see the Earth, only 240,000 miles away. I must say, though, that the communications were outstanding. I never felt isolated, and I didn't. Everybody has to speak for themselves, but I never felt isolated on the moon at all. We had practice with the delay, the communications delay, one way and two ways between the Earth and the Moon of about 3/4 of a second, I think, something like that in the system for voice communications. Now the video delay was much longer because of the more complex electronics it had to go through, and we'll talk maybe a little bit about that in a moment. Next slide. Gene Cernan is here testing out the lunar rover. That was an outstanding vehicle for field exploration. It unpressurized, of course, other than the fact the crew was in a pressure suit, a little spacecraft that made it all work. The vehicle weighed about 450 Earth pounds without anything on it. It got a little bit heavier as we got on it and put our equipment there. It could go about 6 or 7 miles per hour over that surface. Now that doesn't sound like very much, but I'll tell you, when you remember 1/6 gravity, you hit a bump and you're going to be off the surface a bit, and it does seem like it's going a lot faster than that. The front and rear wheels it had front and rear wheel steering, independent suspension, and motors on each of the wheels. Really was a very, very productive vehicle, and a tribute to the people who designed and built it. We would drive this about as I say, 6 or 7 miles per hour over a surface like you see in the background there. We actually had it up to 18 kilometers an hour, which would be about 12 or 13 miles an hour going downhill once. And I think even Gene Cernan regretted going quite that fast. Again, we were spinning pretty hard on that one. Next slide, please. Well-dressed astronaut on the moon, including a geologist, wears what you see here. The suit and the man weighed about 300, and the backpack totaled about 370 Earth pounds, but that's only about 61 lunar pounds. The mass is the same. You have to worry about inertias and things like that. But the weight really makes a difference in how much energy you use. And frankly, with one exception, I never felt muscle fatigue from working, even for being in that suit for almost 9 hours, 3 different times. The muscle fatigue we did feel, though, was in the glove. Was because of the glove. It was in the forearms. And although I thought we were in pretty good shape, very good shape by the time we flew, we weren't in good enough shape to really work hard continuously. You just couldn't do it. Your forearms would fatigue very rapidly because the pressure glove is a pressure glove, and it's a fixed shape. And every time you want to pick something up, it's like squeezing a tennis ball. And so you end up wearing these muscles out quite quickly. The nice thing is that after a night's rest, all that fatigue was gone. There was no muscle soreness. It was as if you're starting all over again. But it is one of the issues with the next generation of suits that we have to do something about. I think we have to make it much more user-friendly. Now, in defense of the current suit, and particularly in defense of the current EVA astronauts, they are much better prepared for work with the gloves than we were. I thought we were prepared, but these guys are in far better condition, much beyond anything that we thought we could reach. And again, I think personal training and personal trainers have a lot to do with that. All the work in the tank, where they do a lot more tank EVA work, pressurized EVA training than we did. And the things that they are doing on the International Space Station are just phenomenal. And you couldn't do that unless your forearms were in outstanding and your whole body was in outstanding condition. So that's a big factor for the future, is that we have to make sure that crews do get that kind of physical training and targeted physical training for these EVAs. The rake you see there that I'm using, we call it a rake. It actually was obviously a sieve. Was designed to get a particular size fraction of rocks that contained a higher proportion than normal of rocks thrown in from other parts of the moon. We were trying to, one way to sample the rest of the moon was to get these little rocks that had been thrown there by impacts elsewhere on the moon. Next slide, please. This large boulder had rolled down the North Massif about 1.5 kilometers. I'm there for scale. It hit a change in slope. Changed from about 26 degrees to about 20 degrees in slope, and broke into 5 pieces there and stopped. It's a rock composed of fragments of other rocks. It's what geologists like to call breccias, so you won't know what they're talking about. But it has told us a great deal about the nature of these huge impacts that have occurred on the moon, and before that occurred on the Earth. Next, please. I hope you can see it better than I can, but that's the same rock there, a big boulder on your left, and there you can see. I hope you can see the trench that it left as it rolled down the mountain, the track, which was basically a trench. And there are my footprints going out of sight and up the other side. Those footprints will stay in some kind of recognizable form for about 1 million years, possibly 2. That's not too bad. Leave your footprints in the sands of time. The only erosion that occurs on the moon, or these systematic erosion, are micrometeorites that continue to hit the moon, and they gradually, over that period of time, will garden the surface or stir it up enough so the footprints will be largely obliterated. Of course, a larger impact would obliterate them much faster than that, but those don't happen very often. Again, this is sitting on a slope of about 20 degrees. It doesn't look that way here, but just because of the way the camera is oriented. Next, please. This picture was taken between the second and third excursions, or EVAs. You can see that we have stirred up an awful lot of lunar regolith, debris. Working around the lunar module. And this is not only an issue for the future visitors to the moon and an outpost, It could have become an issue for us with a few more days of activity. And we're going to have to learn how to stabilize surfaces where there's going to be a lot of traffic. And probably the best way to do that, simplest way, is with aggregate. Once you're processing lunar materials, one of your process streams can be aggregate, and you can cover these areas with coarser rocks, and that'll help that will stabilize it. It's the old principle of macadam. Maybe some of Scots in the audience will know that macadam originally was not asphalt based; it was just gravel based. So an old Scottish contribution to human technology. Also, it's in this soil where the essence of what that book over there is all about, Return to the Moon, is found. It's the solar wind resources, the solar wind volatiles. The most important from an economic sense, potentially to us here on Earth, is a light isotope of helium called helium-3 that is a nearly ideal fuel for fusion power reactors. My colleagues at the University of Wisconsin back in 1985 were so discouraged over the current, then and still current program in fusion technology that the Department of Energy was undertaking that they went back and retreat and actually stumbled across the literature from the Apollo program, the scientific literature. And in one of the first papers ever given at the Lunar and Planetary Science Conference back in 1970 had to do with the presence of these solar wind volatiles in the lunar soils, the lunar regolith. And 13 years later, they figured out that, the Wisconsin guys figured out that this was a very valuable resource that we should pay more attention to. And that's really the basis for that book, is how you would do that. Next slide, please. Yours truly, it doesn't prove I was on the moon, but I seem to have had an awful good time while I was there, and not at all bashful about standing around in my underwear. We got pretty dirty, and although there were no noticeable effects of breathing the lunar dust, and I think that certainly for relatively short missions, it's not something that one should consider a risk. Longer-term occupation and exposure to lunar dust, and it's extremely fine particle size, some of it, that I think we have to be concerned about that. And primarily, we have to engineer habitats and suits so they don't get any dust in them. And so it's primarily an engineering problem for those of you who are engineers. We have to just eliminate that as a potential hazard. Next slide. Next slide, please. Well, we finally left the moon on December 14th, 1972. Ed Findell, whom some of you know, and Ed, you might even be in the audience for all I know. I run into Ed every once in a while. He's still living around here. He was responsible for starting the camera on the rover, ordering the camera to move so it would track our ascent. And we did get an excellent set of pictures of an ascent. Ed had to lead that command by about 6 seconds. He had to 6 seconds before liftoff, he told the camera to start moving, and by the time the signal got there, we were lifting off, and he tracked the camera extremely well. It was really quite remarkable. Next slide. Gene, by the way, tried to get me to go outside and get a really good photograph of liftoff. And I was becoming increasingly politically astute and decided not to do that. Rendezvous. This picture Ron Evans, of course, took from the command module. And that's all that was left of the Challenger at that point, and eventually was crashed into the moon for science to provide another seismic signal to the seismic net that had been left there. Next slide is the command module, and looking at the scientific equipment bay, which is open, and Ron had been running various remote sensing instruments from that bay, and all of the last 3 missions had that bay filled with different kinds of instruments, and it really did provide us our first major insights into the global composition of the moon. and insights which have been further enhanced by Clementine and the Lunar Prospector missions, and now with the European and the Japanese and the Chinese flights around the moon, just an avalanche of data coming in to help, which we can use to help plan our return to the moon with human beings. Next slide. Ron Evans seemed to have a lot of fun while he was alone up there. One of the things, though, he did was to take this picture so that the engineers would understand that they hadn't done everything perfectly. One of the problems with the fuel cells that we had, since it was a source of our water, was that a little bit of hydrogen would leak into the water that was formed by the operation of the fuel cell. And here Ron has made it possible for that, or worked that hydrogen into a bubble so that he could take it back and demonstrate to the engineers that they had missed getting that hydrogen out. The reason it was important to us is that, you know, you eat the food, the rehydrated food, and what goes in must come out, and much to the discomfort of your crewmates. A little added. Now, he's one of the things he's important about this picture is that his experimental materials here is salmon salad. And we almost always use salmon salad for this purpose because salmon salad doesn't travel well. It was almost, I don't know of anybody that asked for salmon salad in their menu. And we were supposed to have control over our menu within the limits of what was available. Well, obviously there was a lot of salmon salad being returned, and it ended up on the next mission. So it kept appearing. So one thing to remember when you go into a museum, and they may have astronaut food here. I don't know whether they have salmon salad out, but you've got to remember that sometimes what is on display is what was brought back, not what was eaten. Okay. That's those of you who may become archaeologists in the future. You got to remember that. The middens may contain some what was not eaten, as a matter of fact. Next slide. This is our entry into the Earth rising over the moon sweepstakes, which was won immediately by Jim Lovell and his crew because they took the first Earth rising over the moon picture. But we think this one's better. I think this one's better, but it'll never be on a stamp, believe me. But it does illustrate, though, more seriously, our new status in this solar system. That we, as human beings, committed ourselves to a gravitational field of another planet, and that was the first time. Apollo was the first time that human beings did that. There was no absolute guarantee that you were going to return, but it broke that bond with the Earth, at least temporarily. And now we know, as a result of Apollo, that the resources are on the moon to live there permanently, independently of the Earth. And then subsequently, we now know that similar resources exist on Mars, although we know less about them at this time. It is, I think, important for us to remember now that the generations that are coming along, maybe some in this audience, are the young men and women that are going to begin to permanently put us on a path to the settlement of our solar system. And this picture is just one symbol of that new status that we have in our evolutionary status, if you will, in our solar system. Next slide. And there's the old moon. It does symbolize a great new understanding of what we now know about the early history of the Earth. It symbolizes a new source of resources for the planet, particularly in energy, and a new source of resources for our exploration of the solar system. Hydrogen, oxygen, carbon, nitrogen are all immediately available to us with just a little bit of new engineering of how processing the lunar regolith. Next slide. We returned, that picture actually of the moon was taken as we were leaving the moon. Now, 3 days later, we've entered the Earth's atmosphere. Our actual entry peaked Gs at 7 times gravity, just for an instant, because we wanted to be sure, of course, we were captured in the atmosphere, and that required then doing that. And then the command module actually was flown by the computer, not by us, although we had that capability. Flown because it at 30,000 miles an hour, 35,000 miles an hour, almost anything is going to have lift of some kind if you orient it right. And the command module did. It had a nice lift vector and could be flown towards where they thought the carrier was. In fact, it knew exactly where the carrier was supposed to be. The Navy learned early on that they better park the carrier away from that point because we might indeed have a carrier landing. At this point, though, we had already gone through the deployment of drogue chutes at 25,000 feet, and then this deployment of the main chutes at about 10,000 feet, and we were moving down towards the water, I believe, at about 16 feet per second, about the rate of a sport chute. Next slide. And splashdown for the last mission occurred not too far from the island of Samoa, and very close to the next slide, please, to the carrier Ticonderoga, which you see off in the distance there, and one of its helicopters now beginning the process of recovering the crew of Apollo 17, and while after the Navy SEALs had done a masterful job of getting the flotation collar out, and also a life raft for us to get into. Next slide. Well, ladies and gentlemen, this is the last slide. I just want to remind you that it was an extraordinary period in human history, that what was accomplished by the generation of Apollo. The history of science, we gained a first-order understanding of the moon for the first time, of another planet, really. In the history of technology, we gained a whole new platform of know-how from which we could reach farther into the future. We haven't optimized yet all of that technology legacy, but nevertheless a great deal of it has been used to better human condition here on Earth. The flag of the United States symbolizes what free men and women can do when they are faced with a challenge that they believe in meeting, and indeed that generation of Americans did meet the challenge. And of course the Earth above the flag there symbolizes that new position that we have in the historic position we have in our solar system that ultimately I'm sure will lead humans to settlement away from the Earth. With that, ladies and gentlemen, I thank you very much, and if there's still time, we'll take a few more questions. Yes, sir.
First of all, I'm not going to grad, so go back.
Yay! I'm not, by the way. I just work there.
Credit, perhaps yourself, for convincing the scientists, convincing the powers that be that a scientist should be part of it. How long did that whole time?
The question is, in addition to a statement that he's a Badger, Wisconsin Badger, the question is, who would gain the credit for deciding that scientists ought to be involved in going to the moon, and me specifically? That's a very long story, and it goes back principally to one person in the several people had an early role in making that happen. Gene Shoemaker was on assignment to headquarters for a year back in the year after Kennedy, within the year after Kennedy's announcement, and he was making putting pressure there, talking about that because he wanted to go. He didn't know that he couldn't at the time, but he wanted to be part of that. There was one of Gilruth's close advisors, Voss, I've forgotten his first name, here are in the Manned Spaceflight Center, and here that was much an advocate of getting scientists into the program. And then in the National Academy, there was Harry Hess, who was at the time a chairman of the Space Science Board of the National Academy. And it's sort of a gradual merging of pressures from the Academy and of interest within NASA that led to, in 1964, the announcement of opportunity, we'd call it today, for volunteers from the scientific community to be in the fourth class of astronauts. Strangely enough, well, by that time, Shoemaker had discovered that he had Addison's disease and would not be able to go. He was 2 years beyond the age limit that was fixed, but I don't think that would have been a problem had he been physically able. But Hess asked him to chair the selection group, the initial selection group. And that winnowed down 1,400 applications to 80 to 16 that were then given to NASA as the Academy's selection. I thought the group was too small. Gene Shoemaker and I argued about that almost to the year of his death, that they should have put a larger group into the mix so there had been more to select from. Because what happens when you take people who are in their late 20s and generally early 30s out of the scientific community, almost all of them have a medical problem. And that's true of almost anybody. They could find something to disqualify essentially all 16 of us. And in my case, I had an intestinal operation in 1960 that rearranged my large intestine, and of course that was unusual. You know, I wasn't a part of the normal human being at that time. Well, the pilots, of course, get into the pilot game 10 years before we were asked to get into it. So it was a dicey thing. But in my particular case, there were 4 geologists in that 16. And all of us had something wrong with us. In my case, the then consulting head of aerospace medicine for NASA, Randy Lovelace, who had, with his uncle, organized the Lovelace Clinic out in Albuquerque and actually had run the early tests on the original 7 group, the group that became the original 7. He contacted the surgeon that had worked on me, Claude Welch, and they got together and decided that not only was I perfectly acceptable, but I probably had a better set of intestines than anybody else in the program. That they would probably function much better in space than most intestines. So the two of them, Lovelace sort of overruled the prevailing Air Force NASA wisdom that, and I got into the program. But I mean, that was just one geologist in the whole program. So if some scientists were going to the moon, it was going to be me more than likely, because and so my job was to make sure that I was absolutely ready, that they couldn't say I was not qualified to fly a lunar module, or at least act as a systems engineer in a lunar module, as well as a pilot could. And I think I was able to do that. But still, if you've read Deke Slayton's book, Deke, he allows in there that he did not recommend me for Apollo 17. He said it was a close call, but the sequence was that Joe Engle would be the lunar module pilot for 17. Well, that was overruled at headquarters, and Deke was. They just, as I understand it, they just told him figure out a way to get to adjust the crews so that I was on that crew. And Deke had 2 choices. One is to substitute the Apollo 15 backup crew for the Apollo 14 backup crew, or to just put me on the crew. And unfortunately, and sadly really for Joe, he made the decision to, either way, but I really sympathize with Joe, but that's the way the decision came down. And the person who probably was most influential, just because I've seen his diary notes up at Rensselaer, was George Low in making that happen. Yes, sir.
Yeah, I've always seen the pictures of the footprints, and you'll see the prints in your photos. if you reach down and grab some moon like that, is it like the ashes from a wood stove, or what's that?
That's not a bad analogy, except that it's very compact and it's slightly cohesive. You know, your ashes and dust, fine dust here on Earth. Every particle has some atmosphere around it, and so it flows. It fluidizes, and whereas the moon doesn't have, the particles are joined together to each other because of unsatisfied electron bonds. There's no atmosphere to join them together or to separate them. So in that case, if you reach down and grab it, it's sort of cloddy a little bit. The best analogy I can give you is damp beach sand. You know, you can scuff it and it'll break apart, but you can also grab it and it'll slightly hold. You can build castles out of it. Well, you could build castles out of lunar soil too. Probably not that cohesive. Yeah, not that cohesive. But you could probably build sandcastles on the moon without any problem. We didn't try it, but I did dig trenches a lot, and the walls of the trenches held up very nicely. So I see no reason why you couldn't. The cohesion wouldn't be enough to build some nice sandcastles. Something for kids to think about one of these days. Way back there. Go ahead. Yeah, in the middle. Yeah. The question has to do with the effects of lunar dust on machinery and equipment, and I would just repeat my earlier comment that good engineering is going to have to keep the dust out of things. It is very abrasive. The lunar rover, for example, functioned extremely well, and the folks at GM and down at Marshall were able to seal all the bearings. To my knowledge, no bearing seal broke, and the rover never showed any sign of abrasion or wear. On the other hand, our pressure suits, where we had bearings on the wrists and on the helmet, you could see the scratches from the dust when you looked at it. We cleaned those between every EVA, but you could still see that we had scratched it. Now, on the other hand, there was no any significant observed increase in leak rate, and that was primarily because all the scratches were circumferential. There were no radial scratches, and so the bearings held up very nicely as a consequence of that. The hatch seal seemed to seal up very nicely with the pressure that was put on it from inside. The limb cabin didn't seem to leak any significantly higher rate for 3 EVAs. What you have to do when you start thinking of an outpost is making sure that you don't let the dust inside, because over long periods of time it will be a problem, and it can even be a problem for electronics if they're not properly potted and things like that. And so one of the first things you have to think about is what's the primary source of dust in a habitat, and it's going to be the suit. And so the idea of having the suit so you get in and out of them with the suits on the outside of your habitat is a very good one. Now, whether we can implement that is something that we're going to have to think about pretty seriously. And then once you do that, you have to say, all right, if I'm going to be there and there's going to be a limit to the number of cycles that a suit can have before I refurbish it, before I have to clean it and refurbish it, then how do I do that? Is that a separate set of suits I have to have in order to go work on suits? Is it a separate, is that something you can bring into your airlock and then clean the airlock? Hey, I'm not going to tell you what the right answer is, but it's one of those things that I think has to be thought through very carefully. But I'm also very optimistic that good engineers will figure out how to do it, and it'll work out very nicely. Can we make a suit so that instead of 6 cycles, which was sort of the limit we felt the Apollo suit was good for, you can have 100 cycles on a suit? Well, I should hope so, and I hope that suit also has a much more forgiving, user-friendly glove at the same time. Yes?
What you think feel about, there's a couple astronauts getting ready to go out on EVA this week. I was wondering how does it feel, and also can you comment on what you think about motivating the public? That's what we are doing this for.
Well, I think the public has gotten increasingly interested in the kind of things that the fellows are going to do here with this EVA and others after it. I tell you, I am in awe of what the astronauts have been doing with space station EVA. I guess that was clear earlier, and it's still because they are. I think it's a much more formidable task than even what we had to do from a physical point of view on the moon. It's really exciting, and what they have done so far in putting the station together is just remarkable. What we have to do is, we being NASA management and some of the advisors, to figure out how in the world do we keep the space station alive and active while we have a hiatus between the space shuttle flights and the availability of Orion. Now, I think there's some options, and Mike Griffin's very, I think, important emphasis on building the private sector's ability to provide services through the so-called COTS program is going to be important, because, I'm speaking a little here from a conflict of interest because I'm a director of orbital sciences, and that's the most recent entry into the COTS effort. And I feel strongly, maybe more strongly even than Orbital does, that the potential of the COTS development is such that you can begin to deliver crews sooner than Orion can. It's a very simple, straight delivery of crews. It's not the sophistication of what Orion is going to be able to do, but I think you can mature the system fairly rapidly. Once you have it developed as a cargo delivery system, then I think you can also deliver pairs of astronaut anyway to the station without any significant increase in risk. So that may be part of one of the way in which we bridge that gap without continuing to be totally dependent on foreign supply of launch vehicles to get crews to the space station. The space station has a tremendous potential for the future, particularly in biomedical research. And one of the things that the NASA Advisory Council has done is formed a biomedical research or biomedical committee, subcommittee, that has been looking very aggressively at that. And one of the things that's come out of that so far is that there now is a meaningful partnership between the Institutes of Health, National Institutes of Health, and NASA to start to really look seriously at what kind of human research makes sense in space, not only to understand long-duration spaceflight, which the station has to help us do, but also to work on issues that further our understanding of human health here on Earth. Weightlessness is a new environment, a new stress environment for human systems. And if you can understand how the human system is reacting to that stress environment, you gain understanding about human systems here on Earth. The most obvious example is that loss of bone mineral is something that happens to astronauts and happens to older people. And space research may well give us not only insights into the basic processes that are happening there, but also in some ways that we can counteract it. As one NIH person said, who's in the bone world of the NIH, said to me, he said, you know, astronauts recover from having lost their bone in space. So we need to understand why, because older folks don't recover from having lost their bone in space. So that's an open question right now, as I understand it. I'm outside my field. Yes, sir.
How would you respond to those people who assert that exploration ought to be done by robots rather than humans?
Main way I respond to whether exploration can be done, should be done by robots rather than human, is that there is a lot of exploration should be done by robots. Particularly that exploration, one, that you can't do with humans because of the nature of the planet. Like, you can't put humans on Jupiter, and for a long time we won't be able to put them on Titan. Those kind of remote environments, dangerous environments, that's exactly where robots do the best job. We know that from Earth experience in the deep sea and things like that. Also, where you can have humans and robots in the same environment, robotic operations are ideal for taking the workload burden off of humans so they can apply what is uniquely human to the exploration activity. It's something robots don't have. Robots don't have a brain that has maybe 3.8 billion years of evolutionary history behind it. Robots don't have, so far, we don't have manipulated appendages that are as good as the human hand, not even close. And thirdly, you don't have this fantastic stereo-optical system that is the human eye, all coupled through the brain into a remarkable exploration machine, if you will. And what you want to do is maximize the use of the unique human capabilities during exploration, and one way you do that is relieve them of routine duties that robots can undertake. Do we understand how to do that yet? I don't think so. I mean, field geologists, for example, taking my own experience, here on Earth, don't normally have a robotic assistant with them. Now, part of that may be cost, but it's also a question of how do you learn to work with a robotic assistant and not use up more time than you would just doing it yourself. It's a challenge. I'm not saying it can't be met. It's just right now I couldn't tell you how to do it. I wouldn't know, right? If you took me in the field and I had a robotic assistant, it would take me a long time to figure out how I was going to use that robotic assistant. But doesn't mean I couldn't do it. It just means that I don't know how right now.
I believe the point is not whether robots are useful, but whether humans are needed.
Well, I think they're needed. I mean, what I'm saying is they're unique capabilities. If you really want to explore and be prepared for the unexpected, you use humans. Not only is it, I think, technically a much more cost-productive way to do it, it's emotionally much better. And people who ask that question very often are explorers in their own laboratories. They would never, we get a lot of scientists who ask that question. And laboratory scientists, and they would never even consider having a robot do everything in their laboratory. They just don't make that translation to human exploration away from the laboratory. And they're basically the same thing. Human beings have unique contributions to science and to understanding and to operations as well that so far are not something robots can tackle. They can do a lot of remarkable things and will do even more remarkable things in the future. But I'm skeptical that you're ever going to find a way to duplicate where you can use humans to duplicate what humans can do. One more question, I'm told, and then we'll sign some books. We got a young person somewhere, young, even younger than you. How about right there? Yeah.
If you could change anything on the lunar rover, what would you have changed?
If I could change anything on the lunar rover, what would I have changed? That's an easy one. I would have had a source of consumables on the lunar rover so that I could use those consumables in the suit when I was driving and not breathe out, use up the consumables I had in the backpack. And I think that's if we go early on in the Constellation program on the moon with unpressurized rovers, which I tend to prefer, at least early on. Later on, I want pressurized rovers so I can go farther. But then I think you need to have those consumables on the rover that you can. And one thing you have to do is qualify